In this video, I'm going to show you how to integrate rational functions using the technique of partial fractions. So say we want to compute this integral here of a rational function x plus 8 over the product x minus 1 times x plus 2. Now this integral looks pretty tricky at first sight, but there is a way to make it easier using the technique of partial fractions. Now the idea behind partial fractions is that whenever we have different linear factors in the denominator of a rational function, like here we have the two factors x minus 1 and x plus 2, both of which are linear factors. Whenever we have that situation, we can break up the rational function into the sum of reciprocal functions. In other words, we can take that rational function, x plus 8 over x minus 1 times x plus 2, and we can break that up into the sum of two fractions. One fraction is going to have the first factor as a denominator, x minus 1. And at this point, we don't know what the numerator is. Why don't we just call it a? We'll solve for that later. But the idea is we can break that rational function up into the sum of this reciprocal function, a over x plus 1, plus another reciprocal function, which has a denominator of the other factor, x plus 2. And we'll just say the numerator is b. So partial fractions just states that you can do this. There's a way to choose a and b so that this rational function is equivalent to the sum of these two reciprocal functions. But of course, it's up to us to solve for a and b. So that's the question. How do we solve for a and b in this equation? Before we get into solving for a and b though, the reason why partial fractions is helpful is that we know how to compute the integrals of reciprocal functions. The integral of a over x minus 1, for example, would just be a times the natural log of x minus 1. So if we can write this rational function as the sum of two reciprocal functions, and then stick it back in the integral, we'll be integrating the sum of these two reciprocal functions, then the integration will be easy. It'll just be a bunch of natural logs. So really the only obstacle in our way is how do we solve for a and b? And it turns out there's a nice little trick that you can do to make this easier. The trick is to first multiply by the denominator here, x minus 1 times x plus 2. We'll just do that on both sides, times x minus 1 times x plus 2, and do that on this side also, times x minus 1, x plus 2. So then, of course, x minus 1 cancels with x minus 1, and x plus 2 cancels with x plus 2, and this left-hand side is just x plus 8. For the right-hand side, there's a lot of canceling that happens also, and to be very explicit, why don't we just write it out entirely? So a times this product over x minus 1, write in the product x minus 1, x plus 2, and then plus b times that same product over x plus 2. All we're doing is distributing this product to a over x plus 1 plus b over x plus 2. And then we see that some things are going to cancel. This x minus 1 over x minus 1 cancels, and this x plus 2 over x plus 2 cancels. So this simplifies nicely. We've just got x plus 8 equals a times x plus 2 plus b times x minus 1. And so you might say, well, this looks simpler, but how does it actually help us solve for a and b? And the answer to that is that it makes it clear what we can substitute for x to eliminate a or b. So that way we can solve for the other. Remember, this is an equation that should hold for all x. So if we substitute, say, x equals negative 2, so that way this x plus 2 becomes 0. If we substitute x equals negative 2, then that should yield a valid relationship between a, b, and some numbers. So let's do that. Negative 2 plus 8 equals a times negative 2 plus 2 plus b times negative 2 minus 1. Negative 2 plus 8 is 6. Negative 2 plus 2 is 0, so this is like a times 0. That's going to go away. And then negative 2 minus 1 is negative 3, so plus b times negative 3. So this simplifies down to just 6 equals, well, 0 minus 3b. Then you just divide both sides by negative 3, get negative 2 equals b. So there we go. Let's circle that. That's important. We're not at the final answer yet, but that's an important step. we know what b is in our partial fractions expansion, and we can do a very similar thing to solve for a. Let's plug in something that will eliminate the coefficient on the b. The coefficient on the b is x minus 1, so to make that 0, we can plug in x equals 1. And then the result is 1 plus 8 equals a times 1 plus 2 plus b times 1 minus 1. And this simplifies. 9 equals 3a plus 0b. And that goes away, so just 9 equals 3a, divide by 3, and you get 3 equals a. And there's our a value. So with that, we know our partial fractions expansion. We know that x plus 8 over x minus 1 times x plus 2 is equal to a, which is 3 over x minus 1, plus b is negative 2, over x plus 2. So we'll just take that and we'll sub it in for our integral here. So this will become the integral of 3 over x minus 1 plus negative 2 over x plus 2 dx. And this is pretty straightforward. This first thing is just 3 times the natural log of x minus 1. And then the second thing, factor out that minus 2, and then natural log of x plus 2. And of course, plus our constant of integration. Now, at this point, we can be done. We can just leave our answer like that if we want, but we can also simplify it a bit. That might be a nice thing to do, write it nice and pretty. And the way you do that is using log rules. Remember that a multiplier outside a log, that can move into an exponent on this x minus 1. So we can write this as natural log x minus 1 to the third. So you can probably see where this is going. The negative 2 here, that can also go as a power on the x plus 2. So plus natural log of x plus 2 to the power of negative 2. And then our constant here, we can actually write this as the natural log of some other constant. And we can make that an absolute value to fit in with the rest of our terms. And the reason why we would want to do that in the first place is that whenever we add logs together, we can write that as a single log of all the inputs multiplied together. So in this case, a single log of all the inputs, x minus 1 cubed times x plus 2 to the negative 2 power times k. All of them multiplied together. And we can clean this up just a little bit more. Let's write it as natural log. Let's move the k out in front, and then put the x minus 1 to the third, and then this x plus 2 to the negative 2, we can write that as 1 over x plus 2 to the positive 2 power. So over x plus 2 to the positive 2 power. And there we go, there's our answer, nice and compact. Now that we've gotten some experience applying partial fractions, let's try it on a problem which isn't so obvious from the beginning. Say we want to compute the definite integral from 1 to 2 of the rational function 2x plus 1 over 3x squared plus 2x. Now this integral looks kind of scary, and this time we don't see any linear factors in the denominator, we've just got a quadratic factor. And furthermore, we only have a single factor in the denominator, so it's not like we can really pull apart the rational function. But that's not too surprising since we haven't even tried to factor the denominator of the rational function yet. Are there any common terms? Well, yeah, 3x squared and 2x both have an x in them, so that means we can factor out an x. Let's go ahead and do that. Integral from 1 to 2 of 2x plus 1 over x times 3x plus 2. And hey, there's two linear factors, x and 3x plus 2. And just to make it very clear that x itself is a factor, I'll put that in parentheses. X is a linear factor just like 3x plus 2 is. It's just a very simple linear factor. Now that we have two linear factors, we're thinking partial fractions. We'll take that rational function, 2x plus 1 over x times 3x plus 2, and we'll split it up over these linear factors. So we'll write two reciprocal functions. One of them will have a denominator of the first linear factor, x, and the other one will have a denominator of the second linear factor, 3x plus 2. And we don't know the numerators yet, so we'll call them a and b. And now we just need to solve for what a and b are. The easiest way to do that, of course, is by simplifying the equation first. And now it's time to actually solve for a and b. And we do that by subbing in x to eliminate each of these terms. I think the easiest one to do first would just be this x term. If you plug in x equals 0, that'll eliminate the b. So let's do that. Let's plug in x equals 0. And then the equation becomes 2 times 0 plus 1 equals 3 times 0 plus 2 a plus 0b. And 0b goes away. We've just got 1 equals 2a. So a half equals a. And now we just do the same thing, but for a. We want to eliminate a by making this 3x plus 2 equal to 0. So let's go ahead and figure out what x we need to sub in there. So what x will make 3x plus 2 equal to 0? Well, just solve this. You get 3x equals negative 2, x equals negative 2/3. So plug that in, and let's just go ahead and simplify this. These are the numerators in our expansion here. So we can write down our expansion. Our expansion is 2x plus 1 over x times 3x plus 2 is equal to a, which is 1/2, over x, and then plus b, which is also 1/2, over 3x plus 2. And this is what we can take and plug into our integral here. So let's go ahead and rewrite this integral. This is the integral from 1 to 2 of 1/2 over x plus 1/2 over 3x plus 2, integrating that with respect to x. The integral of 1/2 over x is, well, we just factor out that 1/2, and then that's the natural log of absolute value of x. And then the next integral, bring out that 1/2 again, and then naively we can write the natural log of absolute value of 3x plus 2. But remember, if you are going to differentiate this term here, you get a 1/2 and then over 3x plus 2, but then the chain rule forces you to multiply by the derivative of this 3x plus 2, which is 3. So we'd get an extra times 3 when we differentiate, and to counter that, we have to multiply by 1/3. And we just need to evaluate this at the bounds and take the difference, the bounds being 1 and 2. Before we do that, why don't we just simplify this 1/2 times 1/3 is a 1/6. So we'll write this as a 1/6. 1/2 natural log absolute value of x plus 1/6 natural log absolute value of 3x plus 2, evaluated at the bounds 1 and 2. So plugging in 2 into here, we get 1/2 natural log absolute value of 2, then plus 1/6 natural log absolute value of 3 times 2, which is 6, and then plus 2, which is 8, and then minus what we get when we plug in 1. So 1/2 natural log absolute value of 1 plus 1/6 natural log absolute value of 3 times 1 plus 2, so 5. Now, natural log of 1 is just 0, so this term goes away. And we can simplify this natural log of 8 a bit. 8 is just 2 to the 3rd, so if we write that again as 2 to the 3rd, we'll be able to simplify a bit using log rules. So 1/2 natural log of 2 plus a 1/6 natural log of 2 to the 3rd minus 1/6 natural log of 5. Log rules say that we can pull out an exponent as a multiplier. So this 1/6 natural log of 2 to the 3rd can be written as 3/6 natural log of 2. So we get our 1/2 natural log of 2 plus that 3/6 natural log of 2. Of course, that simplifies to 1/2. We'll do that in a moment. And then minus 1/6 natural log of 5. And so 1/2 plus 3/6, which is 1/2, a half plus a half is just 1, so this combines into natural log of 2, and then minus 1/6 natural log of 5. And that's about as simple as we can get it. So we'll just leave it like that. Natural log of 2 minus 1/6 natural log of 5.